Hello everybody. In my talk I want to present the results of a joint work with my supervisor Daniel Potts, in which we took approximation methods based on rank-1 lattices and combined them with a certain periodization strategy in an attempt to approximate non-periodic functions. And our setup looks like this. We start with a test function h in a weighted L2 Hilbert space defined on the d-dimensional cube. Then we construct a change of variables from the d-dimensional torus onto the d-dimensional cube and form periodized functions, now called f, just in the L2 on the torus. And the construction is such that the L2 norm of the periodized function is equal to the weighted L2 norm of our initial test function h. And the ultimate goal, as I told before, is to approximate such possibly non-periodic functions on the d-dimensional cube. And we do this by making use of the existing theory for approximating functions on the torus. For those, we have fast algorithms and also approximation error bounds that we want to transfer to classes of functions in these weighted L2 spaces. So at first, I will repeat some main ideas for the approximation of functions defined on the torus and show you the fast algorithms. Then we will discuss what kind of transformations we considered and also what kind of properties have to be fulfilled in order to transfer smoothness properties of these general functions over to the periodic functions. And ultimately I will show you how we eventually transfer these results from the torus over to the cube. So at first, let's go to the known theory on the torus. The torus, in our case, is identified with the interval -1/2, 1/2. And we consider at first trigonometric polynomials of this form, where we sum over some non-empty but finite frequency set I. And at first we want to evaluate such polynomials, and we define rank-1 lattices. There we need a generating vector z that is then divided into m equal parts and in a sense wrapped around the torus, which we can see here. We take 1, 7 as our generating vector, wrap it around the torus and divide it into 57 equal parts. On the other hand, another task is the reconstruction of these coefficients, which we can do in a stable and unique manner for particular choices of the frequency sets, which we'll discuss later on. And then we need fast algorithms. And for those, we need the following crucial idea. When we take such polynomials and evaluate them at a rank-1 lattice node, at first it looks like this. And then when we actually compute those frequencies times lattice points expressions, we will observe that these will only be integers that repeat itself sometimes. Hence, we can group some of the corresponding Fourier coefficients together and ultimately end up with a one-dimensional Fourier sum. Hence, we come from a d-dimensional expression and simplify it to a one-dimensional expression. And therefore, we also only need a single one-dimensional fast Fourier transform, which is fantastic. So in matrix vector notation, this summarizes as follows. So for evaluation, we simply have P equals Fourier matrix times the Fourier coefficients. And on the other hand, the Fourier coefficients are equal to 1/m times the adjoint of F times P. And for our reconstruction, the unique and stable one, we need a reconstructing rank-1 lattice denoted like this, where I is chosen in such a way that F star F is simply an identity matrix. And now for general classes of functions, F in L1, we have approximants Si lambda, which denotes the usual Fourier approximant, but now with approximated Fourier coefficients Fk lambda hat, which are approximated Fourier coefficients with respect to rank 1 lattice nodes. And now I told you before, we need a specific kind of frequency set, and these are hyperbolic crosses. Those are simply nodes in Z to the D, which are filtered by this weight function, where we take the entries of K and form a product of the maximum of 1 and the absolute values of the entries of this K. And in case of D equals 2 and N equals 16, we end up with this set. And based on this weight function, we can define function spaces. One is A beta, which are just L1 functions, where the norm is now the L1 sum of the absolute values of the Fourier coefficients weighted with this weight to the power beta. And of course, accordingly, we can define Hilbert spaces, H beta, which are the L2 functions, where the norm is now the sum of the square sum of now the weighted expression, the weighted Fourier coefficients. Okay, and for these two function spaces, we have error bounds. So my colleagues, my supervisor Daniel Potts and my colleagues Camara and Fogmar showed that if f is in A beta, which is the L1 case, then you can show that the approximation error in the L infinity norm is bounded from above by n to the minus beta times some constant. And some years later, Camara and Volkmar joined with Tino Ulrich and Glenn Bierenheit, and they showed in the L2 case, you can form a similar upper bound by considering f now in h beta with beta greater than 1/2, and the L2 approximation error is then bounded from above again by n to the minus beta times some log expression and some constant. And so for functions, periodic functions on the torus, we have fast algorithms and we have these two approximation error bounds, and those we will adapt later on. But for now, we go to the next topic of the actual transformations that we want to consider. And I define a torus to cube transformation as follows, where the univariate transformations have to be continuously differentiable, invertible, and increasing, where I want a boundary condition on the first derivative of each of these components, which says that at the boundary points, I want them to be 0. Okay, and then the inverse, the first derivative of the inverse transformation will be denoted by rho, which we call density function. Okay. And then, as I showed you initially, when we go from the weighted L2 norm of H and apply our torus to cube transformation, we can rewrite this new integral as a simple L2 norm when we define f to be this expression. Okay. And now to show you an example. First, we have a logarithmic transformation, which is a composition of the tangent hyperbolicus with the parametrized inverse of the tangent hyperbolicus, which simplifies to a parametrized rational polynomial. And indeed, the first derivative of those go to 0 as we approach the boundary points if eta is greater than 1. And I will show you the effects of this parameter in a moment. Another example is a static transformation, which is simply the sine function. Okay, and to have a look at them and compare them, here we have in blue the static sine transformation, and here we have the logarithmic transformation for eta equals 2 and eta equals 4. And as we observe here in the first derivative, they all have the 0 boundary condition, but with increasing the parameter, the first derivative decays faster and faster into the 0 point at the bounds, which is a crucial property that we need to discuss the smoothness preserving properties that we want these transformations to have. And so we need another function space, which will be the Sobolev space of mixed smoothness, which are the L2 functions, where now the norm is based on the derivatives of the function f in the L2 norm. And the question we wanted to answer is, what do we need in order to have a periodized function f to be in such a Sobolev space of a certain order? And in one dimension, the conditions that we proved look like this. Essentially, we take an H in our weighted L2 space that is additionally n times continuously differentiable. And we could show that our periodized function is indeed in Hm if, on one hand, the transformation itself is a m times continuously differentiable, and we need the derivatives of the square root to be in C0 up to order m, which means they have the higher derivatives still have to go to 0 in the boundary points. And to show the effect of the parameter, let's have let's calculate the concrete bounds for these parameters. So we consider now a simplistic case where omega is just 1, a constant function, and we take the logarithmic transformation from beforehand. And now the task is determine the values eta such that this function is in Hm. So for example, we want this transformed function to be H2. And then our conditions tell us that the boundary condition, the 0 condition on the derivatives of the square roots is fulfilled if each of these parameters eta is greater than 2m plus 1, which means if we want f to be in H2, we need each of these etas to be greater than 5 or equal to 5. No, not equal to 5, exactly greater than 5. That's the crucial point of this property. So for example, we need 6. And if we want it to be in H1, we need it to be greater than 3. Okay, and so what this means is by increasing this parameter in each coordinate, we can control the smoothness of this periodized function. Okay. And next up, what does this mean for actual approximation properties? I need the following norm equivalence of the norms, the norms that we've seen so far. So on the left-hand side, we have the Sobolev norm based on the derivatives of f. On the other hand, we have this norm where we summed the weighted Fourier coefficients. And those are indeed equivalent if beta and m are the same natural number. And now we can summarize our procedure as follows. We took a non-periodic test function h, created a transformation that fulfills some conditions, and then we have a periodized function f, which is in some Sobolev space Hm, meaning it is also in this h beta, which then allows us to use the approximation error bounds that I showed you initially. And so we now only have to go backwards by reverting the change of variables. And this looks like this. So now we apply the inverse transformation and get a description of the basis function of our weighted L2 space, which look like this. So beforehand, we only had a Fourier system, and now by applying the inverse transformation, we have these weighted and transformed exponential expressions. And with this orthonormal system, we also have in a completely natural way Fourier coefficients, now with respect to the weighted L2 function, and we also have an approximant, where we take the approximated Fourier coefficients and the new orthonormal basis system. Okay. And this ultimately allows us to also rewrite the former approximation errors in now terms of the cube. And in case of the L infinity arrow, we need an additional weight in order for those expressions to be finite. Okay. And finally, I want to show you some numerical examples. Again, we stay simple with a constant weight function omega and consider the hyperplane, so a simple hyperplane in the d-dimensional space. And we will compare the static sign transformation, and I will just show you the actual effects of the variable logarithmic transformation. But before we go into the numerics, I will shortly show you at least one of those transformed functions. So here in the non-transformed version, we have a simple two-dimensional plane. And once we increase the parameter eta and apply the logarithmic transformation, we can observe that the boundaries are indeed zero everywhere. And with increasing parameter, the essential information is pushed more and more towards the center of our domain. And also another effect that we'll see, the decay into the boundary will be smoother and smoother for increasing parameters, as we showed before in the theory. And now for the numerics, we take our new approximation errors that we calculated and show it the relative errors. On one hand, we have this weighted L infinity error, and then we have the discretized version of the L2 error, and we will evaluate both at 100,000 random nodes in the d-dimensional cube. And now we end up with these kind of graphics. So let's start in the top left. We are in 2 dimensions and compare on one hand the sign transformation, which is here, the yellow line, and the blue logarithmic logarithmic transformation with eta equals 2. And both are equally good or bad, which is good because those are in the same smoothness class. Then once we improve or increase eta to 4, we have we increased also the smoothness order, which means we have a faster decay, which we observe here. And if we go to eta equals 6, we add another smoothness degree, and the decay is initially worse, but eventually will be faster. For the L2 error, we have almost the same picture, where again sign and logarithmic transformation for eta equals 2 are the worst. Then for eta equals 4, it gets better, and for eta equals 6, it gets even more better. And in dimension 5, the calculations took much longer, which means I can only show you up to eta equals 4, but same result, sign transformation, and for eta equals 2, they are not that good. And once we increase the parameter, the error decay gets faster, which becomes more apparent down here in the L2 case. So finally, let's summarize. So we took our existing theory for periodic functions on the torus, where we had fast algorithms and error decays, and could set up classes of transformation functions which allow us to control the smoothness that we actually can create in our periodization attempt. And so ultimately we could adapt not only the algorithms, but also the approximation error bars. And for more details, I want to refer to a former work of us where we discussed the case going from the torus to R to the D. And for more details on this talk's topic, I refer to our recent preprint. Thank you for your attention.